When we started the semester, we started with electrostatics. We started with the definition of electric charge. And then we moved to the idea of electric potential and electric voltage. Finally, we went to another step, and that was that we started talking about electrodynamics. So moving electric charge, and this led us into the idea of electric circuits. Now, an interesting thing is the next section of the class involves magnetism. And so, interesting thing about an introduction to magnetism is that if you got a magnet, then you have a little magnet here, and you put it near another magnet, you can sometimes find that the ends of the magnets attract each other and sometimes they repel each other. You take a magnet and put it near something that's like iron, it's attracted to that. Okay, and so this is an interesting sort of thing. Now, what happened was that the whole study of magnetism was originally just using a handful of weak permanent magnets, lodestones. These are naturally occurring magnetic ore. They also found that if you have something that's iron or something, and you take a magnet and rub against the iron thing, then the iron piece will become magnetic. And so there were several things here that related, and so, but the whole idea of magnetism turned out to be what appeared to be an entirely different concept. And so physicists were studying magnetism as an entirely separate concept from the way that they were studying electricity. All right, so the idea of magnetism being something different, and but there were some similarities in here. Okay, so one of the things that we learned was that electricity was bipolar. You had positive and negative, and magnetism was bipolar. Okay, you had two types as well, and they were generically called north and south. Just like with electricity, likes repel and unlikes attract. Well, that's interesting, because if you have a bar here and you suspend it, you know, what's going to happen is it's going to twist in the Earth's magnetic field. One end of it that's towards the north, we call the north end of the magnet. The end that's towards the south, we call the south end of the magnet. But wait a minute. We've got Earth. Earth has a geomagnetic north pole, geomagnetic south pole, and if you put a magnet here, the north end points towards the north pole, the south end of the magnet is attracted to the south pole. Okay, that's why we call it north and south pole. Okay. Well, wait a minute. We know that likes repel. So that means that the Earth's magnetic north, geomagnetic north pole is magnetically a south pole, and the Earth's south geomagnetic pole is magnetically a north pole. So this is the north pole of the Earth, that's the south pole of the Earth, geographic poles. Okay, and so, but the geomagnetic poles are magnetically reversed because the north of a magnet points north and the south end of a magnet points south. Something a lot of people don't really think about. Okay, so this is some of the beginnings of studying these fields right here. Okay, now comes yet another interesting discovery, and that was the relationship between electric and magnetic fields. Okay, and this was actually discovered by physicist by the Christian Ørsted. This was discovered by a Danish physicist by the name of Christian Ørsted. Now, he was actually at the time teaching at University of Paris, and he was teaching about electric and magnetic forces and gravity. And he was pointing out that gravity is only one way. So gravity only attracts, okay, whereas electricity and magnetism are both bipolar, and they both either attract or repel depending on circumstances. And so he was making an analogy that the two are the same. Now, as he was doing this, as often happens in physics classes, that you finish one topic and start the next topic, and sometimes you have just one or two more things you want to say about a topic, and so you'll do a transition like mid-lecture. And so he was doing that. Rather than finishing his electricity chapter and then starting magnetism, he decided, he had one more thing to say about electricity, then he started magnetism. Now, in those days, instead of students doing labs, what happened was they just watched the professor do an experiment. And so in order to do electrical experiments, you needed a huge amount of electrical current in order for the wires to be glowing red hot so the students could see where the electricity was going. And so what he did was he had a huge voltaic pile to make a huge amount of electric current going down his wires. Now, when he did this, he had these wires running across his table, and near those wires he had compass needles here, and the compass needles he was going to use to put near other magnets and bring them in and show how they deflected. But when he turned the current on in the wire, the compass needles started to deflect a little bit. Turned off the current, the compass needles swung back and pointed north-south. Turned on the current, they deflected again. So what happened was he discovered that electric currents create magnetic fields. This was a huge discovery. Now, at that point, he totally botched the explanation to why that happened. But still, it was a huge discovery that electric currents can create magnetic fields. And so with that, then he began to investigate this. Not very long thereafter, along came another physicist, Michael Faraday, who was also studying the whole idea of magnetic fields making electric currents. And then we had other physicists coming in here, and they started studying this as well. And they started to realize that, in fact, it became considerably more complicated, that electric fields and magnetic fields both act on electric charges. So this makes us realize that electric forces and magnetic forces are really part of the same thing. They're different aspects of what we call the electromagnetic force. So the electromagnetic force. Now, for static electric charges, you apply an electric field, they have a force that makes them move. Okay. Now, likewise, static electric charges make static electric fields. Okay. Now, with magnetism, the realization came that electric currents, so electric current is moving electric charges, they make magnetic fields. And so what happens is that means a magnetic field would act on a moving electric charge. So a magnetic field does nothing to a static charge, but it only acts on moving charges. A moving charge makes a magnetic field. So the changing electric field is what's producing the magnetic field. Likewise, a changing magnetic field produces an electric field. And so the two are different aspects of the same type of phenomenon, or same type of force. Okay, so that became the key. The symbol we use for magnet